Now let's take a look at the transformations of shrinking and stretching, which are probably the hardest of all of the transformations. So the hardest thing, I think, to kind of wrap your mind around is the difference between a vertical shrink and stretch and a horizontal shrink and stretch. So obviously a vertical shrink or stretch is going to deal with the y values, because if we look at our x, y axis, the y is the vertical axis. And if we want a horizontal shrink or stretch, then that's going to be a b value, because that's going to change along the x-axis. So we have some very specific rules about whether or not it's going to make it bigger or smaller. So if a is greater than 1, and so again, if we're looking at an f of x function, it would be a of f of x. So the a is on the outside of the function, taking the whole function times some value. And that a, if it's bigger than 1, then it's going to stretch it. It's going to stretch it vertically, which means if I had a box like this, it would stretch it vertically in this direction. It's harder to see when you're looking at, say, a line. It's harder to tell what has happened. If a is between 0 and 1, well, then that number is smaller than 1, and it's going to take what was already maybe a small figure and shrink it down a little bit. So we get the idea of a dealing vertically. If we're dealing with a b value, if b is greater than 1, and again it's going to look like y equals f of bx, so you're going to have some b inside your function, like y equals, say, 2x squared. That would be a b value, where this one would be y equals 2 times x squared, where only the x is being squared. This would be a of 2, this would be b of 2. So that's the difference between a and b. B is going to shrink it or stretch it horizontally, which means this direction. And I'm not going to even attempt to draw those pictures, but you get the idea. But if b is greater than 1, it's actually going to shrink it horizontally, which means it's sort of going to shove it closer to the y-axis. And if it's between 0 and 1, then it's actually going to stretch it horizontally. So let's take a look at two very similar functions and how they are very different in terms of the transformation from the original graph. Keep in mind my original graph is y equals x cubed. If I were to graph the parent function, it would look something like that. It should go through right at 0, 0. You get the idea. Now I have to determine which one of these is an a and which one of these is a b, and what do I do with those values? Well, as I can see on my first function, g of x, the 2 is not being taken to the third power. I'm taking the whole function of x cubed and taking that function times 2. That means a is 2. Please remember that with a, we're going to multiply the y values by a. That's what we do when we have an a value. My second function is 2x is being cubed, which means 2 is being part of the function, and that's a b value. So here b is 2. Whenever we have a b value, we're going to divide the x values by b. So that's why when b gets very large, everything else gets really small. So let's take a look at my new transformed functions, the ordered pairs. I'm going to start here. If an a value tells me to multiply y by a, that means x doesn't change. I'm not going to do anything with my x values. With my y values, I'm going to multiply them by 2. So negative 8 times 2, negative 16. Negative 1 times 2, 0 times 2, 1 times 2, 8 times 2. There's my new function. And again, that should be giving me a nice stretch in the vertical direction. For my second function, I'm looking at my x values changing, which means my original y values right here will remain the same. But I'm going to take my original x values and I'm going to take them all divided by 2. So negative 2 divided by 2 is negative 1. negative 1 divided by 2 is negative 1/2, which I could write as negative 0.5 if I'd rather. 0 divided by 2, 1 divided by 2, 2 divided by 2. So here's my transformations. Let's see if those make sense in Desmos. So let's take a look at the functions that I've graphed here. And I've already graphed this first function. Notice I haven't pressed the little dot next to these, so you can only see my original function. So this is what that original function looks like. This is the parent function. You can move this out of the way if you need to. So this is what my normal function would look like. And then I want to see what happens if I have an a value of 2. Now we already talked about the fact that that would be a vertical stretch by 2. So notice when I click on that, and again I can go ahead and show the table as well, I do come up with the same values we came up with together by hand. But take a look at the graph as well. It's like I took the blue graph and I took each end of it and I pulled it in opposite directions up and down, which stretched it vertically. So that's what my red one looks like using an a value of 2. So let's get rid of that one for a second and take a look then at the second transformation, which was a b value of 2. Now a b value of 2 is a horizontal change, and it's actually a shrink with a factor of 2. So let's go ahead and look at the values to make sure we did our math right. 1, negative 8, and again if I needed to know what 1/2 was, I could put 0.5, oops, 0.5, and then the negative 0.5, so it will do those calculations for you if you want to verify. But essentially what happened is it took the values and moved it closer into the y-axis. So it kind of shrunk it down to be closer to the y-axis, and that's what happened when we divided by 2. Here's one for you to try, and I've given you a fraction this time to make sure you know how to deal with fractions. So press pause, try this question, then press play to see how you did. So again, first thing I'm going to do is determine which one's A, which one's dealing with A, which one's dealing with B. Just as a reminder, in case we forget things, when we have an A, we're going to take our y value times A, which will either shrink or stretch it, and that means that it's going to be a change vertically. And if we have a B value, we're going to take our x value divided by B, which is going to be a change horizontally. So let's look. I'm going to choose to use blue for this guy. And because the 1/2 on this one is inside the absolute value, that means this is where B is 1/2, because it's inside the function, it's part of the function. Whereas, let's use purple for my other one. 1/2 is on the outside of the function, and therefore in this one A is 1/2. So let's take a look at what my new functions look like using my rules. My rule for B says take x divided by B. It's going to change things horizontally. X divided by B. So here I have the point negative 2, 2. I'm going to take x divided by B. So negative 2 divided by 1/2. Keep in mind, guys, we can't divide by a fraction, so we multiply by the reciprocal. So I'm actually multiplying by 2. But my other value, my y value, will remain the same. So this negative 2, 2 became negative 4, 2. Same thing for the next one. I had the point negative 1, 1. It's only going to change the x values, so I'm going to divide negative 1 by 1/2 or multiply it by 2 to get negative 2, 1. 0, 0, nothing's going to happen to that. But as we can see, the pattern, this is what my new graph will look like. And again, this was a horizontal stretch. Now for my second one, and again, these functions, or these points, this point became this point. This point became this point. We get the idea. For my other function, I'm only going to be adjusting the y value, and I'm going to take y times a, so times 1/2. So for negative 2, 2, it's going to be negative 2, and then times 1/2 gives me this point right here. And then negative 1 comma 1, I'm going to take the y value times 1/2, so it's negative 1 comma 1/2. 0, 0 is going to remain the same. And essentially what it turns out to be, whoops, that was not a point I needed. Let me recreate that line I screwed up. What turns out happening is we do get the exact same graph, but don't be fooled, because this point became this point, and this point became this point, and this point became this point. So even though the graph itself looks the same, the transformation of the graph was not the same.